What's up, everybody? So the time has come for me to show you what the final end product of the toilets for space design has come to. So here it is. There was actually a ton of work that had to go into this, as far as conceptualizing designs, finding the best designs to meet all the requirements in not only making CAD models and 3D models to help portray what your design is, but there was almost a whole essay you had to write explaining how your design meets the requirements and how it goes above what NASA is looking for. So it wasn't a simple, here, I'll throw it together and submit it and hope they like it. No, I put a ton of work into this and a ton of thought. And my whole idea was that I wanted to share it with you, which is kind of why I made these videos. Hopefully that it inspires you to, get out there, think outside the box, and, just come up with some cool stuff to help mankind, help the world. It doesn't have to be about space. It can be about, getting water to parts of the world that don't have clean water. Finding ways to grow foods for countries or communities that don't have food to sustain the population. Engineering is much more than just coming up with cool stuff. It's coming up with ideas and processes and products that can help the world. And I hope this inspires you to let loose of your creative side, so that that one little dumb idea that you have might be the one that saves a whole country from starvation. Think about that. Now let's get on to the Lunar Loo design. So this is the PowerPoint that I put together for the submission. So the first thing I need to do is get a list of choices and things that I need to solve a problem for. Went through it in another video, so you can go back and watch the series and it'll list pretty much everything I have here. But what you're here for is the design. There it is. I came up with 2 designs, and I did that because I started on one and I started fine-tuning it, and I got to the point to where I thought, is it gonna work? So I made a rendition of it just in case, give NASA a choice. They like to be able to choose some stuff, but the overall design's the same, but the air intake is what changed. So the first one you see here, Rev 1 is the primary design, and Rev 2 is the secondary that changes the intake for the fan. And that's pretty much the only difference. You see on Rev 2, I don't have the lid or the other stuff. That's because it's irrelevant. I don't care about it. I already portrayed all that in Rev 1. In Rev 2, all I was pretty much portraying is the change in the air intake. So with that being said, let's talk about the design. Components. Everything has to have components. Without components, you have nothing. Without matter, you have no materials. It's the same thing. Each product is made up of a set of components, and each of those components serve a purpose for the outcome. So starting from the top, we're going to work our way down. So we have the vomit tube. This was the extra credit that NASA gave you if you can make a way for an astronaut to vomit into the toilet without literally sticking their head in. And my solution was to have a tube right here in the green. It's mounted in a pivoting ball, so that when it's flipped up, it opens up a port into the storage tank. And it's also connected to the fans and the motors, so that when it flips up, it flips a switch and then activates everything, and everything turns on. And when it's closed, it seals off. So when it's not in use, it's just like the lid being closed. Next one is the fan and the filters. So we need the fan to circulate air. Not only circulate, but we're using a fan to create a vacuum. And in this design, I wanted to create a closed loop vacuum system that was also able to use positive pressure. So not only does it pull air, it also pushes air, which makes it unique and hopefully a little bit novel that they'll like. I like that idea. Filters are a must. Anytime you're moving air in any type of septic or storage unit of waste, it's going to stink. So any way that we can reduce the odors, the better off we are. That's the lid. We have to have the lid that's sealed off when it's not in use. A seat to sit on. A fan to circulate the air. A bowl for them to go in and to funnel everything into the waste storage unit. Deflector between Rev 1 and Rev 2. Rev 1 has a deflector shield. And this deflector shield, I'll explain later, helps guide the waste so that it does not enter into the fan system, which was one of the reasons why I came up with Rev 2, just in case if that became a problem. Perforated ring, which is novel to only Rev 1. Fan ducting, DC motor to operate a turntable, gear-driven turntable, the storage tank, and vanes within the storage tank. And that pretty much makes up all the components besides the outer shell. So the components of Rev 2 are pretty much the same, and the main differences are the fan ducting. So the fan ducting is routed almost the same, but the intake's in a different spot. And yeah, so that's about it. So how does it work? You want to know how it works. Because without it working, it's not going to work. So I wanted to work on a closed loop air system. And that means that when I pull air into the bowl, I don't have to exit it out back into the cabin area. And the reason I did that is because if we ever get any type of urine or moisture in that air, we would have to separate it from the air before we put the air back out. Because we don't want to be putting a bunch of urine spray out into the living quarters. Because it's a itty bitty space. And another reason is because those fans that operate those separators suck a ton of power. And with the 70 watts of power limit, we didn't have the room to keep adding more and more electronics onto this. So what I did was go with a closed loop system. So the air it pulls in, it filters through and then blows it back down the top. So as you can see, the fan draws air down through this perforated ring. And the idea behind this is that as the air draws down, it pulls the waste. So as the waste goes down this tube, it's gaining acceleration and momentum. And in zero gravity, we know that once we start something in motion, it's going to remain in that motion until it is acted upon by an outside source or an outside force. And the idea behind this is as we gain momentum and velocity through this tube, once we reach where the intake is here, that it has enough velocity and momentum that it's going to shoot past the opening for the intake before the intake has a chance to pull it out. And once it's passed, it's going to reach the vanes of the storage tank. And now here's where the second part of the idea works. I have electric motor that is mounted that turns a turntable. And it spins it, and this turntable is where the storage unit mounts onto. So I'm actually going to use centripetal force inside the storage tank to contain it and move it. So once the waste gets into the storage tank, it's going to be spinning. The vanes are going to catch it, pull it to the outside and then down to the bottom. And the whole time that this is spinning, no waste could ever make its way back up into the bowl because that would be a mess. So give me a thumbs up if you think that that was a good idea. Let's see. So airflow. How does the airflow work? Well, we have both positive pressure and we have a vacuum. When the fan turns on, it's actually going to pull air down in red. So the red is our vacuum. And you can see it goes into these ports and through this ducting in blue. The fan pushes it up into a hollow cavity seat. And once it's in the seat, there are ports on the other underside of the seat that align where the bowl is. So the air comes through the hollow cavity into those ports and then blows positive pressure back down into the bowl. So we get this constant loop, which first it keeps from putting all that air back out into the urine or waste that does get up in there. Either the filter is going to catch it, filter it, or it's going to be blown back in. So this eliminates the chances of having any type of waste put back into the cabin. And as for the Rev 2, so I thought, what if there was a chance that we could not physically keep the waste from entering into the air ducting? So I moved the intake ports down here to the bottom. So it actually pulls up from the top outside of the storage tank. So when we pull air, so let's say the fan turns on, we get the red here in arrows. We create a vacuum. So we're pulling stuff in, it circulates back up, and then the positive pressure blows it down. So it goes down, it has to go down into the storage tank because that's where the source of airflow is coming from. But the magic of the vanes in the storage tank and the centripetal force of the tank spinning, once it enters into the tank, the vanes and the centripetal force push it to the outside, down to the bottom of the tank where it stays. So we can always keep this top area clear so we don't obstruct anything else going in there and we don't cause any type of waste to go back up into the air circulation system. Bonus. So waste movement. I already went over a little bit about how the waste moves, but this gives you a general view of what the waste is doing. In red, you see this is the waste that is moved by airflow. And in blue is where it transitions to where the waste is moved by the tank in terms of centripetal force and the vanes. The vomit tube, it's sealed when it's closed. When you open it, it has that same limit switch so that once it opens, it turns the fan and the motor on. And it opens up the port once it's fully open. You vomit in there, it gets all sucked in there. When you're done, you close it and you're ready to go. So you don't have to stick your head in the toilet if you get sick. Bonus points. This gives a breakdown of the requirements NASA had and how my design has met those requirements. So can it function in microgravity? Yes, we use both vacuum and positive pressure flow to move the waste. So we're not relying anything on gravity to move any of this waste. Lunar gravity, we do have gravity on the lunar surface, but we're not going to rely on it. It's going to help us since everything is in from a top to bottom flow. Any type of gravity is just going to assist in what we already have, which is going to make it work in both. The physical constraints, it does have a mass of less than 30 kilograms of Earth gravity, and that is roughly, I think, about 30 pounds. And given the input materials that I had for it are a little on the heavier side, they do still fall within those requirements. So if we do want to make them lighter, the possibility is there by using different materials. The volume, so the whole toilet itself is less than that 1.5 foot by 1.5 foot cubed. Operation constraints was 70 watts of power. So the DC motor at full power, now this is at startup, is 58 watts, but running power is a lot less than that. The fan operates on 12 watts, and when you combine those two together, even if you turn on both simultaneously at the same time, we still will not exceed that 70 watts max. Noise levels. So since all of our components, like the fan and electric motor, they're inside the shell, I guess you would say, of the toilet. So we could, if we have trouble with sound levels, we could insulate it. But being inside a shell, they're not noisy anyway. The fan had a sound level of 50 decibels, and that's direct pass. So that's me looking right at the fan and it running. But with it being within the components, you have the filter on it that's going to dampen the sound. It's going to have to pass through the shell, the fan ducting, and all that. So each thing is going to keep reducing the sound levels. Starting with the 50 decibel sound level, I roughly estimate that we're going to be dropping it pretty close to probably a 20 to 25 decibel sound level. The DC motor, again, it's estimated between 40 to 50 decibels direct path, and being mounted inside these components, again, we're going to continue to reduce the sound levels. And with that being said, if we do have anything with being close to that 60 decibels, we have plenty of room for insulation and dampening procedures to further reduce those noise levels. I don't think the sound level requirement is going to be an issue with this design. And it can accommodate female and male users. And this is because I tried to keep the whole design as close to operational as a toilet here on Earth. So you go in, you open the lid, you sit on it, make sure everything's lined up, and then you go. And the airflow pulls it away from you and into the storage tank. When you're done, you wipe, you do all your cleanup, and everything goes into the tank. So there's nothing different besides how the waste moves in this toilet than there is on a toilet on Earth, besides no water. We don't use any water. So here's a list of the performance requirements that NASA put out there, and the calculations were made for the storage tank when given that up to a liter a day per use, averages 6 uses per crew, the amount of fecal matter expected per crew, and we were given the expected time of the missions. So with all that, we can calculate the density of the feces and the urine, and we calculate how much total volume area that is expected to take up. And then from there, I calculated how big my tank needed to be so that it can meet the needs for storage for the whole mission. This way that NASA astronauts do not ever have to change a storage tank during a mission if it ever became an issue to where they needed more room or they wanted to change out halfway to eliminate some other issues. That size of tank can always be adjusted and changed. It can be made bigger, smaller, depending on what you want to do. These circumstances and requirements, I went ahead and calculated to hold the max duration of the mission so that it would never have to be changed. As far as the stabilizing urine goes, the ideas that I had was either a pre-treated tank that had a solution in it that lowered the pH of the urine so that whenever you went, it was already in there. You didn't have to do anything else. Another idea was to have a storage tank inside the cavity of the toilet and a hand pump so that whenever an astronaut does go to the bathroom and has urine that enters into the storage tank, that one squeeze would give one dose of this solution, and that would lower the pH for that one dose. And over time, you just keep adding per dose, and it wouldn't take any more power. It's hand pump, manually operated, so the only difference would be is one you have to manually do, and one it's already in there and you don't have to do anything for it. So to keep the crew safe if there was ever a failure, the whole system is a closed unit, which means that it can operate standalone by itself, connected to nothing else. And when it's not in use, it is completely sealed. If there was ever a failure with any component within the toilet, all the components are serviceable without being exposed to anything regarding the storage tank or the bowl. So everything could remain sealed while it's being serviced. And that is done by an access panel in the front will let you access the electric motor. There will be an access lid on top that you would pull off, and you can pull the filter straight out and then have access to the fan. So if you change a filter, it's a quick 1-2 minute job. Get to the motor, quick job. And if the fan ever failed, you just pull the filter out, and then the fan access is right there and easy to change. All in all, the whole design is simple, easy to use, easy to maintain, and easy to repair. What more could you ask for? So let me go ahead and show you real quick. This is the actual submission. As you can see, you had to upload some type of art to kind of give you a little advantage of saying, oh, look at that. That looks cool. Let me see what that is. You got to give a little background about yourself. So a little bit about me, where I'm at, what my engineering background is, and all that good stuff. And this is a complete overview. So this will be like the back of a book. If you want to know what the book's about, you read the back. So this is what that is. A picture of your design. So pretty much just an overall picture of this is kind of what it would look like. And then it goes into details. So each requirement that NASA had, you have to go in and physically write out and tell them how it would meet that requirement, what makes it different than everything else. So here it's why would it work in both micro and lunar gravity? Why would it work for a male and female? Does it have the opportunity of maintaining the power requirements and noise requirements? How does it stabilize urine? Can it accommodate 2 crews for 14 days? If it can, how? Why? I mean, they want a lot. And if you don't put a lot of detail, you're probably going to get looked over. And the more detail you can put, the better idea that they're going to have when they look through your submission. You also have to go into your TRL rating, which is pretty much, is your technology mature enough that it's going to be able to be put out there in the next 2 to 3 years? Or is it going to take years and years and years of refinement and continued changes to get it out there? So if you put in here a bunch of technology that no one knows anything about, they're probably not going to use it because they don't have the time to put into it to get it to work. So the more you're on the side of having something that with a little bit of analysis you can get it to work, the better off you're going to be. And then I put all my files into a zip file, and that's all my CAD files, my presentation, my assemblies, and all that goes into one file, submit it, and a little bit about if you were a winner. So there you go. So that's pretty much the toilet. I hope you enjoyed the process, and if you look forward to more videos like this, and more series like this of doing these type of crowdsourcing projects and competitions, let me know in the comments below if you have any ideas or any crowdsourcing sources that we could go to and find some more challenges. But if you like this video, if you like this toy, if you think it's going to work, give me a thumbs up. And please don't forget to subscribe. It really helped me out, and I appreciate your support. And I'll see you on the next one. Bye.